Okay, my name is Grimm. I'm a software developer since 1999. I have a passion for C++, and of course I should also say for Python. And today I want to talk about concurrency, in particular in C++ 20. Meaning I talk about C++ 20, but I give sometimes a few ideas what changed in between 11 and 20. Okay, so this is my idea. I want to talk about this stuff here on the right. You see? Here we are. Here we are. It's a bit difficult. On atomics, semaphores, latches, barriers, cooperative interruption, and finally stood jthread. Okay, first of all, a little bit of history. We have atomics in C++ since 11. Okay, what can you do with atomics? They provide you atomic operation, which give you synchronization and ordering constraints, which also hold for the non-atomics. This is the key of threading. You have atomics, which provides synchronization ordering constraints. And this synchronization ordering constraints also holds for non-atomics, and therefore always when you do stuff like threads, tasks, here we have it, threads and tasks, here we are, mutexes and locks, condition variables, under the hood atomics are running in making this thing thread safe when you do it right. So the basis of all is atomics. And essentially we have two different, let me say, kinds of atomics. First of all, we have an atomic flag, and second, we have stood atomic, which is a class template which has many different partial and full specializations. Atomic flag is something extremely special. Why? This is the only thing we have which must be, or which is guaranteed to be lock-free. So stood atomic with all its specialization, such as pointers, integral types, user-defined types, floating point types, and smart pointers, they can use internally locks for synchronization. Even they are called atomics. Only atomic flag is the only one which is guaranteed to be lock-free. Okay, so far not so interesting, but I will come to the interesting stuff. What you see here is, since 20, we have atomic floating points and atomic smart pointers. I will come to them later. Okay, so what can you do with an atomic? With an atomic flag in C++ 11, this is an extremely, how should I say it, poor data type. You can only say test and set or clear. So it has essentially two states, similar to a Boolean, to atomic Boolean. You can set the value, and as a return value, you get back the old value, or you can clear it. This is what you can. You can, for example, not read it without modification. And then we have stood atomic. And on stood atomic, we have a rich interface. We can say, is this implementation lock-free? We can load it, we can store it, we can exchange to atomics. We can say compare exchange weak, compare exchange strong. I will come to this both member functions in a few seconds. We can say fetch add, fetch sub, or we can increment, decrement them. The difference between fetch add and fetch sub is fetch add, fetch sub returns the old value, and increment and decrement the new value. They increment the value or add something to the value, but they return the old value. Okay, what is the most important function on this slide? Compare, exchange, strong or weak anyway. These functions are called typically CAS, compare and swap. They are the cornerstone for any kind of atomic operations you want to implement. When you see here, you see there's no multiplication, there's no division. But I can easily implement it. When you get my slides, I have all the examples running here in the Compile Explorer. I hope this works. Exactly, it works. by the way, oh, this is big enough. I was not sure how big I should make it, but it's big enough. Let's see what I do here. I want to implement an atomic multiplication. So an operation which applies a multiplication on atomic which is thread safe. Let me put it this way. So I have an atomic int, and I want to add multiply it by 5. And you can see from the right it works. So out of 5 I got 25. How is this working? This is my fetch mult. By the way, this entire algorithm would be C++ 11-ish, but I used a concept in C++ 20. So this is the only reason why this is a C++ 20 thing. Okay, this is a concept, or you can also say a type constraint. So what does this function do? It takes an atomic by reference, something it wants to multiply, the atomic should be multiplied with, and here's the operation which is performed. And this is how you typically do with atomics. First, I now recognize that I forget to explain you how this compare exchange strong works, but you will see it in a few seconds. First, I load the old value. I store it here. Then I compare the old value, you see this old value from here, with the current value of shared. When they are equal, I in an atomically step exchange the value of shared with the value old value times multiply, because I want to multiply in an atomic step. When they are not equal, meaning something happened between here and there, some other thread kicked in. When they are not equal, I update old value to shared. This is how this operation works. And there's one piece missing to understanding it. When this operation is successful, it returns true, if not false. And of course, I return the old value. This is how fetch add works. Therefore, also my fetch mult is working this way. So I implemented an atomic, or let me say, a log-free algorithm based on compare exchange strong. And this is always how you deal with that stuff. When you do concurrency, or in particular dealing with atomic stuff, you store or you remember the state of the word, then you try to modify the state of the word, but only if the preconditions are still valid. You check here if shared is equal to old value. When they are not valid, you update your assumption about the word, which is the old value, to the current state of the word, which is the new shared value. So you have to think, when you do concurrency, and here in particular when you do work with atomics, in transactions. Okay, so far I assume this was boring, right? Now I jump to 20. I only wanted to provide you a little bit of background. Oh, wrong thing. Okay, wrong direction. Here we are. With C++ 20, the interface of atomic flag and std atomic was extended. And here are the two most important points. Now you can notify, or you can notify using atomics. You see, notify all, notify one, notify all, and wait. I will show you a few performance numbers in a few seconds, but this is what you can do. You can now use atomics to synchronize threads, for example. And the behavior here is a little bit, let me explain how this works. When atomic is equal to val, this call blocks. It only does not block when atomic is not equal to val. This is how it's defined. Okay, let me show you an example. And you know what? I'm a big fan of condition variables, and now I show you a few workflows all which are easier to use and faster than using condition variables. And here we start. I assume you know what a condition variable is, or? Have a look. Here I have a small workflow. I have a thread which is waiting for work, and I have a thread which which prepares data. Let me put it this way. So I have a let me say a producer-consumer workflow. T1 wants to consume something what T2 produces, right? So this is what is performed. Set data ready, puts a few values inside a vector. You see, this is an atomic bool, initialized with false. It puts a few values in a vector, says, hey, I'm done with my preparation. Then it stores the value true inside. Previously, it was false, you know. And afterwards, sends a notification. And this wait call here waits for this notification. But this wait call blocks if atomic bool is equal to false. And you see, this is the, let me say, the starting condition. And therefore, I have a pretty simple notification mechanism using atomic bool. I will use the same workflow a few times also with condition variables to see how nice this is. And then it waits, and when the notification appears, it puts the first spot to 2. Okay. This is what you can do to make it explicit with C++ 20. Go on.
The example you showed, it only works once, right? If I want me to do the operation a few times?
You have to put, for example, when you do it the way I did it, you have to put the bool back to false or something like that. But I will make an example in a few minutes in which you see how you can do it more than once. I will implement a ping pong game. I had a class 2 days ago. Ping pong means table tennis, ping pong, forward, backward. So you have to be, yeah. Is there a guarantee of the ordering? No, of course not. Sorry?
So if I wait in order, there is no guaranteed order of the notification?
No, there's also, when you send, no. So in my case, it was a one-to-one communication, which is fine. But with a one-to-many, you have to think about other things. We have other things, to which I will come later. Okay. Okay. You all know we have in C++ 11 shared pointer. Or as the people from the C++ community say, shared putter, so don't be irritated. Shared pointer. There's a meta rule in concurrency, and this meta rule is the following. Be as local as possible, be as constant as possible. This is the meta rule for concurrency. And a shared pointer breaks this by design, because it shares. Or let me put it in the words from Tony van Eert, one of my favorite quotes. Forget what you learned in kindergarten. Don't share. Most important rule about concurrency, but shared pointer breaks it. Therefore, a shared pointer needs an exact semantic regarding concurrency. And with C++ 20, we got an atomic shared pointer new specialization, atomic weak pointer. So this is a C++ 20 extension. And let me say it explicitly. So far, no implementation of atomic shared pointer or weak pointer is lock-free. They all use under the hood a lock. This is still a problem. A friend of mine, Timo, tries to implement it. I hope he will succeed in one point in time. But once more, this is not lock-free, but at least it's thread-safe. Because a shared pointer has a strange semantic regarding concurrency. You may know it. The control block is thread-safe, but not the resource. Just keep that in mind. So increasing the count, decreasing count, and deleting the resource is thread safe, but not the access of the resource. Okay. There are essentially 3 reasons for this atomic shared pointer. 3 reasons. Let me put it here. First of all, consistency. You may not know it, but put it back. Shared pointer was the only non-atomic variable in C++11 on which you could apply atomic operation, load and store. This was an extreme exception of the rule. So out of consistency, we need atomic shared pointer. We need it also out of what? Correctness. You see what? When you do this, now compiler will protect you for doing this, but this is maybe a threading issue. But so what you should do is, of course, this. Therefore, you want to be correct not on discipline, but on type level. But in 11, it was based on discipline, so that you not use this one, but use this one. You see, atomic store. And the next point is, why do we need that? Because of speed, because of performance. Why? It makes no sense to make a shared pointer by design thread safe, because in the most cases you use them single threaded. Therefore, we need an explicit type. This was the atomic shared pointer and atomic weak putter. We got also atomic ref. This is pretty interesting. So far, only a few people use them. We have specialization for atomic ref. For all the type without the smart pointers, we have also for stood atomic. But here's the main point of atomic ref. It means it protects you, or it protects also the referenced object. And accessing the referenced object is no data race. This is atomic ref. And once more, it supports the interface of stood atomic, so is log-free and all the stuff. Load, store, compare exchange strong, compare exchange weak, exchange, and what else. Let me show you an example. Now I have it. Okay, I have something, believe me, expensive to copy. Just an example. Assume this is expensive to copy. Then I create a few random numbers between begin and end, only to calculate something. This is not the important part. Here's the important part. I have expensive to copy, which count takes by reference, you see, here, by reference. It creates threads in some 10 threads. Each one increments the counter by this number given between 100 and 200, just an arbitrary number. And here's the essential point. This counter here is shared. You see it. Without a protection mechanism, this would be a data race. But I put this counter in an atomic ref. And now when I execute it, I don't care about the result. When I execute it, this is thread safe. Even 10 threads use this counter concurrently, which would be, of course, a data race. Why not? Yeah?
Can't you just pass a reference to just an atomic?
A reference to, be careful. When you copy references, or when a thread takes a reference, it decays the referenceness and you become a copy. So from the performance, from the safety point of view, you are fine, but you will not get the result you expect. This is a little bit tricky. Just study the implementation of stood atomic, what it does with its arguments. Sorry, stood thread or stood gthread, what it does with its arguments. This is a little bit a pitfall. At least it's not a data race. But this is pretty nice. And only let me show it to you. To be honest, this is not mine. When you do concurrency, you should always use a tool which is called thread sanitizer. I have to put on my glasses. F-sanitize. I only want to show you that this program has really an issue. So you see, this is of course no proof. We got the same result and so on. But when I remove this atomic ref and make it only an int, have a look. Now we get a little bit of red colors. Wait a second, here we are. Thread sanitizer complains there's a data race. Only to make this obvious, without atomic ref, this is a data race. Concurrent reading and writing means data race means your program has catch fire semantics. When you execute it, your PC can catch fire. I was really lucky, I saw. Okay, anyway. Okay, continue. We have also a nice, let me say, synchronization mechanism in C++20, which are semaphores. A semaphore is essentially a thing. You start with a specific counter. Each time you acquire the semaphore, the count is decreased by default by 1. Each time you release it, it's increased by 1. When the count is 0 and you want to have this semaphore, you are blocked. You can also see it a little bit such as a generalized mutex. Okay, and we have a specialization, binary semaphore. So we have a counting semaphore and a specialization, a full specialization. Oh, this is long for 1. Okay, so this is essentially what you can do. Hey, sorry, I have this one. This is essentially what you can do with a semaphore. You can release it by default, updating it with 1. You can acquire it, you can try acquire it, and you can also apply time boundaries. This means a time duration, which is a data type from C++11. This means a time point, which is also a data type from C++11. Let me show you an example. I hope you have still this example in mind, which I showed you before, about this producer-consumer workflow. Here we are. The same workflow such as before. Waiting for work, set data ready. You see? And here you see this is all what you have to do. By default, I have a counting semaphore initialized with 0, but it can at most have the value 1. And this guy wants to have it, but cannot have it because it has already the value 0, therefore it's blocked. It's blocked until this guy here says release. Now it goes from 0 to 1, and this guy can take it. So this is the same workflow such as before, but this time implemented with semaphores. I will show you in a few seconds a pretty ugly way to implement this workflow with condition variables. And then we come to your point, ping pong or performance measurement. Because I love to do it, I can implement this in 5 different ways, and I want to know what one is the fastest and what is the easiest to read. Okay, let's go back. Yo,
The feature that lets you send 1 to a template is it C++20?
what? A little bit louder.
When you send 1 to counting semaphore in the angle record, is it C++20? It isn't a type, it's a number.
Wait a second. Can you be a little bit more specific? Maybe you have a little bit of misunderstanding. Let me show you to you. Is it what you can see here?
In line 7.
No. This is a counting semaphore. This is such as I would say std vector of int. This is, I'm not sure if I should say it, a 2098 feature. There are 3 different things with which you can instantiate a template. Types, int, vector int. Non-types, essentially integrals, such as numbers. Std array of int, comma 5. Here you see the 5. And the third thing is you can also instance a template with a template. So these are the two different types a template can have. So it's a 98 feature. It's nothing new. Maybe unusual, but not new. OK, let me jump back. And now I come to my favorites, condition variables. I should not say it, but I don't say it. I don't like them. Let's be a little bit friendly. I don't like them. So you have condition variables. A condition variable is an extremely simple means to synchronize threads. We have a sender-receiver workflow to implement. You use a condition variable. The only way you can do it in C++11 when you want to have more than one synchronization, use a condition variable. When you only want to synchronize one, please use a future promise pair. This is way easier to do. So, but when we want to play ping pong, we have to go this way. So this is a condition variable. A condition variable can play both roles, the role of the sender and the role of the receiver. You see, you can say notify one, notify all. Oh, this is easy. And you can wait. This looks easy, but is not easy. You see, there's a lot of stuff here. First of all, wait has to use a lock, to be precise, a unique lock. And second, there are these 3 dots. And this is the fun stuff. Condition variable can be victims of 2 extreme ugly phenomena: spurious wake up, lost wake up. What's a spurious wake up? Sorry about this strange story. What's a spurious wake up? You are in bed, you wait for the alarm clock to go. And it was not alarm clock, it was the cat scratching at the door. So this is a spurious wake up. The wait has the impression there was a notification, but it was no notification, it was a background noise. So what do you do when you are in bed? And, sorry? Exactly, you need a predicate. You need to check anything what happens before the alarm clock. This could be alarm clock or something else. This is spurious wake up. The next thing is even more funny. This is lost wake up. Lost wake up means you go to bed after the alarm clock went. This is, to be serious, a deadlock. You wait for something which never happens, will never happen anymore. And here you do the same. You also check the clock, before you go to bed. These are 2 ugly phenomena, and there are condition variables. You have to deal with them when you use condition variables. I will prove it to you in a few seconds. So let's continue my fun. Let me explain the workflow. You see how complicated this is. I have here notify one. I have here waiting. Let's discuss this workflow. So both are running in separate threads. Let's discuss this workflow from the wait perspective. We have only 1 hour, therefore I make it short. There's way more to discuss here. So what is happening here? You wait. Before you wait, you have to log a mutex. Then when you wait, what you do first, you check this condition here. You see this is a predicate, a function which returns true or false. Because what? Here you check if this, oh, I'm too small. If this already happened here, ready equal to. When this returns false, you know you went to bed, but the alarm clock so far didn't ring. Then you sleep, you sleep, you sleep. You immediately, by the way, release the lock, because when not, the another guy could not take it. Here, this mutex. So you sleep, you sleep, you sleep. Then you get a notification. What you do now is you log once more. You first check if return ready is set. This gives you the guarantee that not a cat was the reason for the noise. So when the return ready is set, you know it was really the alarm clock. When the return ready is not set, it was a spurious wake up. Then you fall asleep. Maybe return ready is false. You fall asleep. Sometimes in the future, you will be awoken once more, and now assume it was really the clock. So this is kind of a simplified presentation of this workflow. There's more to it, believe me, but I will not go into this direction. And here is the same function. Once more, this producer-consumer stuff from before. But you see, waiting for work set out ready, now using condition variables. I have the log guard, which protects my data ready. I notify, and this guy is waiting for it. And here's my point. I cannot prove it on Compile Explorer, therefore I will do it locally. Here's my point. When I don't use this predicate here, which is possible, I am a victim of lost wake up. And essentially, I have a 50-50 chance of a deadlock. Because when the point is the following. When the signal is first sent before the waiter is in the wait state, the signal is ignored because there's no memory involved. You don't believe me? Let me show it to you. Here, I remove it, you see? Now I remove the predicate, which means now I'm a victim of lost wake up and spurious wake up. Now let me compile this program. Only to be sure, I should save it. Let me compile this program. And now let's have fun. A deadlock. We see here the output in a wrong sequence. First, we should see the sender before the waiter, but the point is standard cout is flushed, therefore there's also a small issue. But what you see here, this is a deadlock. Let me do it once more to see it more. Now you see it better. First, the notification is sent, and then the waiter is in the wait state. And now it waits for the notification, which will never appear once more. Once more, 50-50 chance. And this is the reason why I dislike condition variables. They are terribly complicated to use. Right. How can I kill this program then? C. I have to kill my program. I have a deadlock. How to kill it here? I forgot it. Control what? Damn. You should never do live coding, in particular when you are used to Linux. Let me make it a little bit bigger. Was there a question?
Yes. How is this different with STD atomic?
Because STD atomic, you will see it in a few minutes, they have a kind of, how should I say it, a memory. They will notice when the notification happened before you are in the wait state.
So signals cannot get lost?
Exactly, this is my point.
About the spurious wake-up?
As far as I know, not. The only victims of spurious wake-up is, I showed you compare exchange strong. This compare exchange weak could be victim of spurious wake-ups. This is the reason you use it always in a loop to be safe of that, but not for this notification stuff. Okay, now I'm back in the old state. I promise this was the last deadlock I produced. Okay, let me go back. And now we are ready. Now we are ready to play ping pong. Now I have a small experiment. Always when I have a new feature, I'm curious, what is the fastest way to do it? And of course, by the way, one step back. First, your program should be correct, and then it should be fast, and also correct. So what is the correct way to do it? And what I do now, read these numbers with a little bit of salt. What I do now is I play a ping pong game. I have two threads, forwards, backwards notifications. How often? Let me see. 1 million times. So I have a ping pong game, and I exchange the ball 1 million times. And I do it with condition variables, atomic flags, and also one atomic flag, with atomic Boolean and a semaphore. Okay, let me show you the different implementations. Here we are. Here. I'm sorry to say it, but this is a little bit difficult to read. But anyway, here we have condition variables. So what I essentially have is the following. I have two functions, a ping and a pong function. And I measure the time you see here, and you see there. I measure time. Thread T1 performs the ping, thread T2 the pong function. And this is what they do. First of all, I have a count limit of 1 million and an atomic counter. Okay. And I stop the game when the count limit is, when counter reaches count limit. Let me put it this way. And now what I do is the following. I have two condition variables. One is waiting, so cont var1 is waiting, but here cont var1 is notifying, and the other way around. So let me put it, I think I can make it a little bit smaller. Is it fine when I make it a little bit smaller? I hope this works for you. Now you can see all of it. You see this is totally symmetrical. Here I wait with cont var1, here I wait with cont var2, here I notify with cont var1, here I notify with cont var2. So it goes backwards, forwards. And here I switch data ready. I change it from true to false, true to false. And in the condition here, in the predicate, I check if it's false or if it's true. So how does this play start? Initially, where is my data ready? Here we are. Initially, data ready is false. Meaning this guy is waiting, you see, because it's not true. It's waiting. Afterwards, it puts it to false, sends its notification. Now this guy can run, and the other way around. So I always put the value fourth back between true and false. I am not sure if this explanation was good, but I assume you get it. Now I have a ping pong game. And the question is, how fast is this? Don't take these numbers too seriously. On Windows, it was 0.7 seconds. On Linux, it was a virtualized machine. But it was pretty slow. So this is my first ping pong game. It should only give you rough numbers and rough ideas about performance. Then let's consider the second game. The second game is the following one. Where's my second game? Here's my second game. Let's use an atomic. Was it flag or? Let's use a flag. Here I use atomic flag. It has the state cleared. And what I do is the following. This here blocks here. This blocks when the state is cleared, which is here meant to be false. So this blocks when the state is false. When the state is false, so this continues when the state becomes true. When it becomes true, I put it back to false and I send a notification. The notification this guy is waiting on because this guy here is blocking on true. So essentially, I do the same, such as before. So similar. Initially, it's set to true. Test and set puts it to true. Meaning when it tests the value true, this call is blocking, but this call can run. It puts it to false, sends the notification. Therefore, it has false. Therefore, this guy could run, and it puts it back to true and notifies back. So this is the way how this notification goes. I use an atomic flag, and honestly, this is way easier to read. There's no unique lock, no lock guard, no critical section, nothing of that. Okay. And of course, this is pretty fast. You see, on Linux, more than 10 times faster than this condition variable. Once more, measure it by yourself. You have the programs. I always measure with maximum performance, but once more, the Linux guy is a virtualized PC. Okay, let's do it once more. Let's do it once more. This time I use an atomic bool. This looks pretty similar. I have atomic bool initialized to false. Essentially, here I wait for false. Here I wait for true. If successfully, I change it to the other value. So this can pass when atomic bool is false. Therefore, I put it to true, and I send a notification. And here the other way around. So absolutely symmetrical. And you see, I think this is pretty nice to read.
Should it be true and false and false and true?
What do you mean by true and false, false true?
Because you set it to the other way around every time.
Let me explain it once more. Maybe I used the wrong words. I put it here to true. When this is true, this guy here is blocked. You see? But this guy can pass. It puts this to false, sends notification. Now this guy can pass. Maybe I explained it the wrong way. But I think when you see this pattern, this is pretty easy to understand. Once more, if you don't like it, you should love condition variables. And now to my last example, and then you are totally done with ping pong. And this is a semaphore. I have two semaphores, both initialized to 0, and they can have the value, at most a value 1. And here's what I do. I first release signal to ping. Means it goes from 0 to 1. Meaning this guy could acquire it. It increased the counters, and then it releases the other one. You see, I use two semaphores, but essentially I do the same. Forwards, backwards, forwards, backwards.
Why is it faster? It's still putting the...
Wait a second. Here are the numbers once more. Only rough numbers. But what astonished me extremely was that semaphores are really, really fast. They are in the ballpark of atomics.
It's not busy loop, right?
Sorry?
It's not a busy loop, it's sleep.
We have no busy loop in C++. You have to do it by yourself.
Yeah, so what you showed it's sleep. Actually, when it's waiting for the semaphore, it will block.
Yeah, of course. When you observe the CPU, it will not go to 100%.
Will go to 100?
Will not go to 100%. This would be a busy rate. Okay, but my point is, here you have the numbers. And what you can see here is the following. Condition variables in any case are the slowest one and by far the ugliest one. Anyway, I don't have so many bad adjectives in my mind. I don't like them. But anyway, don't use condition variables. In 11, you have to do it because you cannot do it in another way. In 11, you have to implement ping pong using condition variables. Sorry to say that. But when you are 20, you can do it in different ways. And all of the ways are nicer to read and faster. Question in the back? A little bit louder. Can you explain what? once more.
Why the Linux time is slow? It's because it's virtualized. It's not an actual.
This is a virtualized PC. Don't take the numbers too seriously. I was also a little bit astonished, but I can say to you, I give a lot of classes. The numbers in Linux are similar to the numbers here. Not the absolute numbers, the relative numbers. I only have a virtualized Linux. I cannot do it other way. Yeah?
Did you compare the performance comparison to OS specific semaphores and not the C20 implementation?
No, I only play with 20. I'm totally single-minded. I only care about C++. Okay. Let's continue. We have also nice synchronization mechanisms, which are latches and barriers. Latches is meant for the synchronization of, let me put it differently. You initialize a latch with a number, and the latch is blocked until the number becomes 0. So it's the other way around semaphores. So you have a kind of a barrier, a kind of a latch. All threads have to wait here until the counter becomes 0. It's an extremely simple synchronization or coordination mechanism. So what you can do, you can say count down. You count down by default by 1. You can say wait, which returns to the counter. You can, so try wait. You can say wait, which means you wait, but you don't affect the counter. You just wait. And you can say finally arrive and wait, which means you count down the counter and you wait. So it's essentially this sequence of calls. Okay, let me show you an example. A simple workflow. Okay, it takes a little bit longer, but we'll see it. So here I have a few workers. Herb, Scott, Bjarne, Andre, and Andrew. All of them have to perform a little bit of work. And here's what they do. These are function objects, you see? Instance of a class for which the call operator is overloaded. So this instance behaves such as functions. I will come back to this. Just ignore this. This was just, how should I say it? This gives me just a guarantee that I have nice output. The key point is the following. When this function object is invoked here, you see, this code is performed, and here you say arrive and wait, which means I start the counter, I forgot to say it, with 6. Each time someone comes here, it decrements the counter by 1 until the counter is 0. So in the first case, it goes from 6 to 5. When it's 0, all can pass this barrier. I say barrier to it, but here it's called latch. And now you see this is the output. First of all, our thread say work done, and then they say see you tomorrow. This is an extremely simple synchronization of, let's say, a coordination mechanism. A latch. A latch can only be used once. When you want to use it more than once, you should use a barrier, to which I come now. This is a barrier. So it can essentially do the following things. It can arrive, which means it decrements the counter by default by 1. It can wait. It can do arrive and wait, and arrive and drop. Arrive and wait, of course, means that it first calls arrive, which means decrement the counter by 1, and then waits if the count is not 0. Arrive and drop is more interestingly. Arrive and drop means that for the next iteration, the count is decreased by 1. This means you can do it more than once, this iteration thing. In the next iteration, you are out of the game. This means arrive and drop. If this was too complicated for you, let me show you an example. Now we have a more sophisticated workflow. we have full-time workers and part-time workers. So far we have nothing. Now we have it. We have full-time workers and part-time workers, you see. Help, Scott and Bjarne are full-time workers, and they only work in the morning. Andre, Andrew, and David. And let's see what I have here. Once more, I have a barrier initialized with 6. Now I start all my workers, the full-time workers and the part-time workers. The part-time workers say arrive and drop. So it means in the first iteration, meaning here and meaning there, each thread counts down the counter by 1. It goes from 6 to 0 because I have 6 workers. But this worker here removes themselves from the work. Therefore, in the next iteration, the counter is only 3 because 3 of them said arrive and drop. And these are my part-time workers. And now you see we have 6 guys working in the morning, but only 3 working in the afternoon session, let's say it. And here to make it once more, this is my iteration here, you see. I do it once, and I do it once more. So when you have a job which requires more than 1 iteration, a barrier is a nice thing to coordinate that, yeah.
The barrier automatically goes back to when the counter reaches 0?
It goes back to the old value. Exactly. You can only modify it with this arrive and drop thing. In the draft version, there was a different workflow behind, or they wanted to implement it differently, but this is now how it works.
You don't have the same amount.
Of course, this is a simple example. The point is you have to count correctly here. This is a simple example. In my case, it's right. I start with 6. In the second iteration, I have only 3. But once more, this was an extremely simple use case.
In essence, I don't have the API to modify the number that the carrier will provide.
No, you don't have it so far. The only way I see is to adjust it with arrive and drop, or to go other way and make a second stud barrier or something like that, which you start with a new value. I'm not sure if this is a limitation. So far, these are only toy examples I use here. I'm not sure. But at least barriers and latches are extremely nice things to synchronize work. OK. I'm good in time. I have around 5 minutes left. There's one exciting, a few other exciting features. In C++ 20, we have cooperative interruption, meaning you can ask a thread, please stop. And if the thread is willing to do it, stops.
Like yield.
Sorry?
Yield. Like yield the scheduler.
Now this is different. This is different. I know what you mean. We have also a thread has the yield interface, but this is different. Once more, cooperative interruption. This thing consists of 2 things, or I should say 3 or maybe 4. Anyway, of a stop source and a stop token. And they share a stop state. And the stop source can request, please stop, and the stop token can be used to react to this wish for interruption, but only once. So it can only be used once. I will show you an example. So we have a stop token, which you see here. It has 2 member functions. It can ask if it's possible to stop, and it can ask if there was a stop request so far, if someone asked to stop. This mechanism is built in stud jthread and stud condition variable any, not condition variable, condition variable. Sorry, I say once more condition variable. Anyway, stud condition variable any. But it can be used in a way, way broader context. This is the stop token. On the opposite, we have the stop source. The stop source has a member function getToken to create a token or to create a shared state, I could also say. Then we have stop possible to ask if it's possible to stop. We have stop requested to ask if a stop was already requested. And we have request stop to request a stop. So let me show you an example. Once more, it's built in jthread and in condition variable any. Here I have two threads, jthread and this jthread. This is non-interruptible and this is interruptible. Have a look here. Here's something special. I have a lambda. This is pretty long lambda. I have a lambda which takes a stop token. And therefore, this jthread has the possibility to ask if there was a stop request. Of course, the thread can ignore it. And then when there was a stop request, I say, I don't want to continue my thread of execution anymore. I stop. And now I have the main program, you see. I have the main program. I sleep for 1 second. And then I say request to stop. No, here I say it. To both threads, but not only this one would react because it has implicitly a stop token. And when you see the output here, both threads start, interrupt, non-interrupt, you see. And after the third iteration, a request to stop happens, and only the non-interruptible thread continues to work. Yeah, go on.
I mean, you usually write, right?
But you have to do it manually.
Right.
And here you have a means to express it. In particular, it's a pretty lightweight means to share state and to share stop state and to send signals. So before you would have to do it by yourself because it's an extremely bad idea to interrupt a thread because you don't know which state it is. And here it's cooperative. You just send a signal and the thread has to decide what to do with it. You can also ignore it. And you can only do it once. And there's another facility to it, which I'll show you in a few seconds. You can also register callback, which is called when a signal is sent. Let me show you the next example. I first was also not so, how should I say it? I said this could be a little bit more powerful. But what you can do essentially is to stop all running entity. Have a look here. I have a function which takes a stop token by copy. Stop tokens are pretty, let me explain it from here. First of all, I have a stop source which creates a stop token. And now I can copy this stop token in any place I want to have it, and then I would, at the end, send a signal, request stop. And here you see what I do. I copy this stop token. Stop tokens are pretty easy, pretty cheap to copy. I copy this stop token inside the thread, so I can even use it as std thread. I copy it only just for fun inside the jthread, so I do it now a little bit differently. I copy it inside a std async, so a promise. In here, I react to it. I copy it inside a promise, which I start explicitly in a thread. And I can also use it in the main program. So I can copy it around, and then I can send a stop request. And here's the point I forgot to mention. Here in function 2, I registered a stop callback. This means when this stop token, I get this stop token. When this stop request appeared, I perform this function here. So you can register callbacks. By the way, not only one, as many as you like. There's no guarantee in which sequence they will run, but you can do it as many. You can use as many as you like. And therefore, it's a pretty general mechanism to send signals. And are pretty cheap. So far, a question? If not, I'm almost done. Only two, I think 1 or 2. There's only one small feature, yeah. What do you mean? I don't see it. What's you talked about atomic flag and you talked about the stop token.
It's pretty trivial to ask a thread to stop, especially when you have atomic.
Yeah, but once more, you have to do it by yourself. You have to do it. This is, for me, more a push principle. When you do it by yourself, you have a pull principle. Are you done? Are you done? Are you done? And then you ask for the state change.
It's like signaling.
Yeah. For me, it's more comfortable. And I never measured it from the performance point of view, honestly. But I did some stuff like that in my concurrency book. Of course, you can do it also another way. And this mechanism is by definition of call. The entire mechanism is by definition thread safe, which would also be the case when you would use atomic. Question?
Yes, about the stop token. Faster, you say it's cheap to copy and you pass it by value, but
Sorry?
you say it's cheap to copy. So
Exactly, this was the design goal behind.
but that means that the only owner, it's like a shared pointer in that regard.
Under the hood, it behaves like a shared pointer, exactly.
Yeah, so in this case, it's
It behaves like there must be a shared point inside because it automatically manages its lifetime. And why? How can we do that with smart pointers?
yeah, it's a bit confusing that you have something that goes by value and it's not explicitly a shared pointer, but it's a shared management.
It's just, yeah, you're right. But under the hood, it must be something like that. You have also, when you use a shared future, there must also be a shared point inside, but we don't see it. Question? Do you need what?
If you are waiting with a low latency thread on log, what mechanism would be the best for you?
Sorry, this was too. Can anyone say it a little bit louder? Or? We don't have a mic here.
On a low latency thread, what mechanism should you use?
Waiting on a low latency thread.
The most real-time synchronization.
I never thought about it, but what do you think about my solutions using atomic flag? My suggestion. I don't have another answer for now. Just use this atomic stuff. Okay, wait a second. Let's put this question to the end, and let me just say a few words, and then I will try to understand your question. Okay. Only a small thing, you know it, so therefore I make it extremely fast because we are almost done. Stud thread. When you forget to join a stud thread, it calls stud terminate in its destructor, and which causes stud abort, meaning we have an issue. And now we have a G thread, which automatically joins. Essentially, it uses this signaling mechanism to automatically call join its destructor if it's still joinable. So essentially, this is a G thread has two extensions. One is you can cooperatively interrupt them, and it automatically joins. We say to that it's a RAII base type because it automatically joins. And here's my last point, and then I'm done for today. We have synchronized output streams. Let me skip this. Explanation. Let me show you something. Standard cout is thread safe, but we only have the guarantee that each character is written atomically. We don't have a guarantee about the entire sentence. And with async stream, let me explain it to you here. With async stream, you can encapsulate stud cout, then you write it here, and it is flushed or written down when it synced out goes out of scope, which means here. This is also RAII base type. And therefore, this is an atomic operation. Therefore, we have synchronized output and not an intermixing or intermingling of characters. And you can also do it with a temporary, you see. This is temporary because it has no name. Here I have a name. Here I don't have a name. Therefore, this goes exactly here at a sequence point out of scope. Therefore, here is the output operation happening, and in one sentence. Okay, there's one little small example which I skip now, only to make this point clear. So I'm open for questions.
C++ 23-headed std print, does it have a similar mechanism for synchronization?
I don't think there's a synchronization involved, but at least localization. And C++ 23 is so far, no compiler supports this print or printle function.
Regarding the flash, what about very big sentences?
What about what?
You talked about flash that happens only at the end of the scope.
I said flashing, I'm not sure if this is the right term. Synchronized writing to the output stream, whatever that means.
Okay, so I can output even a very big buffer, very large buffers at once.
I don't know if any limitations are here provided. Of course, we have limitations, but I don't know of them. The main point is the entire sentence is written in an atomic step. This is the main point, which standard COut does not provide you. Sorry?
Can you explain the stop callback again?
Sorry?
Can you explain the stop callback again?
This is pretty easy. You can register a function which is invoked when a request for stop appears. This is all. So you can register an action. And you cannot only register one, you can register, even in one thread, as many callbacks as you like. You don't have a guarantee in which order they will be performed, but you have to guarantee that they will run.
Can I have multiple threads using the same stop code?
Exactly. The point, the synchronization, don't say synchronization. The sharing point is this shared stop state. You have, this is similar to a sync. Whenever you have a std async, you say, std promise, you say get future. In here you say get source. So under hood, I assume these are similar mechanisms. It's more like a shared future to be specific, because a shared future has also internally a shared pointer. And at least this is how I would implement it. Okay. Any question? Okay, I would say I'm done.